We're going to take a look at two more problems involving exponential growth and decay. In this case, we have a new car that is purchased for $28,000 and it decreases in value by 15% each year. We want to write an exponential model for the value of the car. So we can start by making a table. We want t as, instead of x, we're going to use t for time, and that's going to be years, right, because it's decreasing each year. And then this will be v of t, v standing for value, the value of the car. And the reason it's v of t, because the value of the car depends on when we're talking about, right? Are we talking about when we first got it? Are we talking about 5 years down the road? So the value of v is going to depend on when we're talking about, how many years have passed. And we know the first value on our table. At 0 years, the car is worth $28,000, right? That's our given. But what about after 1 year? So what we have to find is, what is 15% of this 28,000? So 28,000, and to find 15%, we multiply by 0.15. That is how much value the car loses. So I'm going to make a third column here. And the third column isn't for points, right? We're not putting like our t and our v or our x and our y value. I need to know what this value was. 42,000. This is how much it lost. This is called depreciation. So the car depreciated in value 4,200. So we need to subtract 4,200 from the 28,000 minus 4,200. That is 23,800. All right. Well, what about year 2? Well, we're going to have to do the same thing. This is the value of the car now, and the car is going to lose 15% of this current value. So it's not 15% of the original value every year. It decreases 15% each year, and it's based off the current value for that year. So we take the 23,800, and we are going to multiply that by 0.15. I think I hit it twice. Let me do that again. 23,800 times 0.15, 3,570. So you notice the amount it depreciated isn't as much as the first year because it's not worth as much. 15% of 23,800 is less than 15% of 28,000. And now we'll subtract. 23800 minus 3570. So the new value of the car is 20,230. All right, same drill. Multiply this new value by 0.15, and now it's going to depreciate $3,034.50. And we'll subtract that from the value of year 2. So 20,230 minus 3,034.5. So that is the new value of the car. 195.50. All right. Same drill. Multiply that times 0.15, and that's how much it loses this next year. Now, here we're going to have to do some rounding because we can't have values in between pennies, right? So this is 32.5 cents. We can't do that. So this is going to round to 33 cents. And now we have to subtract this from the original value. So 17195.5 minus 2,579.33. So now we're at 14,616.17 cents. That was in the 4th year. All right, well, we want the 5th year, so we got to do at least one more year. And so we'll take this, multiply it by 0.15, and that gives us a 2,192.43, right, with the rounding cents. I'm going to move this over here. 2192.43. All right. And we subtract this from the value of year 4. So 14616.17 minus $2,192.43. Now, can we all agree this was a little bit tedious? Not a great process. And then when we look at this process, now they want to know when it's going to drop below 10,000. So we need to continue to do this. Is there an easier way? And the answer is yes. Let's take a look at the equation. So the A value, that's your 28,000. That's your start value, right? And now we need to figure out, well, what is your value here that's supposed to go in the base? I'm going to put T as time. Now, this is where the percentage comes into play. The only problem is, if I do 15%, this is going to tell me how much it depreciated. It's not going to tell me how much value the car has left. And so I just want to take a look here. I'm going to draw a little box here, and I'm going to use this box to show percent compared to the number value. So we have 15% that we're losing. So if we're losing 15%, how much of the car's value are we retaining? So this entire box from top to bottom should represent the whole, all of it. And so if this is 15%, well, this must be what's left over out of 100%. So if we do 100 minus 15, that's 85. So in other words, this car retains 85% of its value. Now for this problem, 15% was 4,200. The 85% should be this value, and I'll show you that that's true. I'm going to take my 28,000, and instead of multiplying it by 0.15, I'm going to multiply it by 0.85. And there's 23,800. So by using 0.85, we automatically know how much we're retaining. So that's what I'm going to put here. So then could I use this equation to get these other values? Let's jump to 5. Let's do 5 years. So we'll go ahead and put in 28,000 parenthesis 0.85, right, inside our, sorry, let me find a good spot for that. I'm going to try that off again. So 28,000, and then here's our 85, and then our caret, and then we're going to put in 5 for our exponent. So let's see how it compares to this value. 12,423.74. Now, this actually would round to 7.5, and here is where we run into a little bit of an issue. Your calculator doesn't know this is money. It doesn't know that, it doesn't know that these values were rounded. It's always going to use all the decimals. And so using this will actually create a little bit of error as we go. And the more years you do, the more error is going to creep into it. Doing these type of things, like an Excel spreadsheet would be the best way to do this. Because on an Excel spreadsheet, you could create a table and make it do all the math for you. And you could tell it to round these values as you go, where the calculator will not do that. But for simplicity, and if we don't need like the super exact answer, we can still use this table. So let's go ahead and plug in year 6. This was year 5. And I'm going to go ahead and go up here, and we're going to change. Is there a way I can get this to point in a little bit more so we can see? Yeah, there we go. There's the caret. There's the caret, and we're going to put 6 now. And we'll hit enter. That's going to be the new amount. So let's add that to the value for 6 years. 60 point. That's going to be 19. All right, I feel like we're close, but they want to know when is it going to drop below 10,000. Let's go one more year. So I'm going to come up here, and I'm going to go and change this 6 to a 7. There we go. In the 7th year, $8,976.16. So during the 6th year, that's when it's going to drop in value below 10,000. So this is what we call exponential decay because the values are going downhill. Now, what would this look like if we graphed it? Now, I'm just going to use, I'm not going to have you graph it on your notes, but I just wanted to, I have a graphing calculator here, so I could just put this in and give you an idea. So here's 28,000, parentheses 0.15, and then we're going to raise that to the x power, and this doesn't do t in this form, so we're going to have to use x as our variable. And then I want to change the windows right away because I'm going to start at 0, and let's go to 10. Sorry, clear that. 0 for the min and 10 for the max. All that's saying is the horizontal axis will go from 0 to 10. And then we're going to have to get our y to go all the way up to at least 28,000. So I'm going to do 30,000. And I can tell it how often to put tick marks. Let's put a tick mark every 5,000. And then I'm going to go ahead and graph this. So that's what our graph looks like. We can see that it's coming down here. So it has that kind of, I don't know if we would call it sloping, like it levels out. Oh, I apologize. I shouldn't make videos this late at night. So the graph does kind of level out. Now, if we went to this side, it would shoot up, but we're not putting in negative values for time. This is really what we're looking at. And we can go to the table, and we can see that the table values are going to be the same as the ones that we have on the table. So there's your 1 through 6. So we can see those values. And then 7. Now, notice it's not showing more than 5 decimals. To get that, I have to go over here, and now you can see all the decimals. So this is limited to 5 characters within the column. So if I want the full values, I have to come down here. So it's a different type of calculator. But we can see that, you know, the values we're looking at, 10,560.19, right, with that rounding. All right, let's go and take a look at the last problem. This is the last problem of the lesson. And for this one here, we're going to look at, turn this back on. We're going to look at money in a savings account. We're going to start with $5,000. We're going to put a 3.5% interest rate compounded yearly. What that means is every year we'll find out what 3.5% of that total is, and we get to add that money into the account. So the bank pays you for using your money. When you put money into a savings account, the bank's like, great, we're going to use this and we're going to lend this money to people. We're going to charge them to borrow this money, and we're going to make money off of it, and we're going to let you have a piece of that back. So when they lend it, they're not lending it at a 3.5% interest. They'll do something much higher, and so they'll earn a bigger interest rate on it, but then they're going to give you a little bit back. So that's why when you put money in a savings account, that's why the saving accounts grows. It's because they're using your money to lend to other people that are going to have to pay back even more money. So it's you get a benefit, the bank gets a benefit. All right, so we're going to start with x and f of x, and x is going to be time. This is going to be years, and then this is going to be your money in the savings account, right? So I'll just put a $sign up there and remind us that's money. Now, at 0 years, this is your 5,000, right? That's your original amount. But what about 1 year? How much money would be in there? So I'm going to make a third column again, and we need to know what is 3.5% of 5,000. So we'll put in our 5,000 times 0.035. That is 3.5% as a decimal. You make $175. That's how much they pay you for that, for keeping that money for a year. So that 175 is going to get added into your account. They pay you that. Now you have $5,175. Okay, what about the next year? How much money would you have? Well, now they're going to give you interest on this amount that they're lending out to people now. And so we're going to take 5,175 and we're going to multiply it by 0.035. So now it's $181.13. $181.13. Now, why is this a little bit more? Well, the 175 that's in here, that's from your original 5,000, but the extra like $6 or so is coming because they're now charging interest on this 175. No, not charging. They're giving you interest on the 175. So if I take the 181.13 and I subtract the 175, you made $6.13 extra because you got interest now added to your account. So 175 is for the 5,000, and then the extra $6.13 came from the extra amount that's now in your account. And that's the one nice thing about interest is it builds. And on the next turn around, not only are you going to get interest for the original 5,000, you're going to get interest for the 175 that was added. You're going to get interest again for the 613. So it just kind of builds and builds and builds. So we'll just do this one more time. So 5,175. Nope, we got to add that. Yeah, so plus 181.13. So this is the new amount in your account. You now have $5,356.13 in your account. And we would just continue this process. I don't want to do this 10 times. I don't think the table is the best way to go. Equation, especially when you want to jump down to values, getting an equation's a much better way to go. So the only problem is with this equation, 0.35 is not giving us the new balance. I want to put a number in here, and we're going to start with our 5,000. But I want a base that is going to cause this to grow. That's going to give me the 5,175. So I don't have to like add it back in. So this is how it works. You're currently getting 3.5% interest. So the amount you should get in the next year should be this 3.5%, plus it should include the original value, the original 100%. So what you're really doing is this value is 103.5% of the original. And I'm going to show you how that works. We're going to change this to a decimal. That's 1.035. Remember, 035 is what we were using before. If I do 5,000, nope, that's 6, 5,000, and we multiply it times 1.035, that's going to give you your 5,175. So that's really what's happening here. So your base, the 1 represents the original amount, the original 5,000, and then what's above that is the percent they're giving you each year. So that's going to be really important to have those values, both the 1 and this 0.35 in the equation. Because if we don't put the 1, this will never give us the values that go in the Y column. Well, let's try it out. Let's go ahead and do 5,000, parenthesis, 1.035. And I'll move this up here just so we have a better view. Caret, and then we're going to put in 2 years. And you can see this matches 5,356.13, right, when you round. So that really does give you your full amount without having to break it up and do individual amounts and adding it each time. So at this point, we can jump right to 10 years, which is nice. So we don't have to go 3 years and 4 years and 5 years. So let's just plug 10 years into here. I'm going to go up. I'm going to come over here. And instead of 2, I'm going to put 10. And I'm going to hit enter. And there's your answer. After this 5,000's been in the bank for 10 years, you'll then have $7,052.99. $7,052. $52.99. So that will be the answer to this first question, how much will be in the account after 10 years. So let's go ahead and just circle that or box that in so we know that's the answer to our first question. Then the next question is, well, how long is it going to take to reach $10,000? Well, on this one, we can just keep plugging in values. We can come up, change the 10 to 11, hit enter. That's closer, but not a lot closer. I feel like we could maybe skip some values. So instead of 11, let's jump to 15. Let's see what happens if we go to 15 years. Okay, that's better, 8,300. So we got a little bit faster, but it's still not enough. Let's go back over here. So we went to 15. Let's go 17 years. I feel like we can still jump a little bit. Well, we're still in the 8,000s. Okay, let's go up again. Is that 15? I thought we went to 17. I must have hit something wrong. Let's do that again. Okay, that's almost 9,000. I'm going to change this just to, we're going to jump to 20 years. Oh, that's really close, right? At 20 years, I'm going to add that to our table. 9,948.94 cents. And we want to know how long till it reaches 10,000. Well, that's pretty darn close. I'm going to say it's going to happen during this 20th year. And so if we plug in 21 years, and there we go. We're now at 10,000. $10,297.16. All right. So just kind of recap on this. With these two problems, we've dealt with percents in both of them. And so what we're really looking at here with this, turn that light back on. Good. If you're dealing with a value where it's depreciation, you actually want to take the percent that it's decreasing and subtract it from 100. So 100 minus our 15, that gave us our 85% that we're using to calculate the depreciation. And remember, if the values are going down, this has to be between 0 and 1. But if you're increasing by a percentage, you're going to need that 1 out front. The 1 keeps the original 5,000, and then this percentage tells you how, adds on the additional amount. So so when you set up those type of equations, that's what it's going to look like. All right, that ends page 3, which is the last page of this lesson.